Welcome back. The next lecture in power electronics we will discuss here is three-phase half-wave uncontrolled rectifier, which is basically the AC to DC conversion using the diodes. Let us see the outline. First, we will discuss little bit on rectifiers. What is three-phase half-wave uncontrolled rectifier? We will do its mathematical analysis, compute the performance parameters. We will see what are the practical considerations required for this, the advantage and disadvantage of uncontrolled rectifier, the applications, and comparison with other rectifiers as well. Finally, we will conclude our discussion. So, we have been discussing the rectifiers for a while in the previous few lectures, and we saw that rectification is basically a process of converting the alternating current to direct current using certain semiconductor devices such as the diodes or thyristors. If we are using the diodes for the conversion principle, then it is uncontrolled rectifiers. If we are using the thyristors, then it is a controlled rectifier. Our focus will be on diodes, that is uncontrolled rectification. Later, we will move to the controlled rectification. So this is our AC input, which is in the form of sine wave, and the AC input is converted to DC output, which is the rectification principle. The DC output that we get may be half wave or full wave, depending upon whether both the cycles are rectified or not. If one of the cycle is rectified, then it is half wave rectifier. If both the cycles are rectified, then it is known as full wave rectifier. The rectification may not produce the pure DC wave because certain harmonics may be present in that, for which we will require filtering action. And here in this topic, we will discuss about half wave rectifier. So it means that only one of the wave we will be using, one part of the wave we will be using for the rectification. And single phase half wave rectifier we have already discussed. Our focus will be on three phase now. So the essential components which are required for DC power supplies depend upon this rectification, and it is used in applications requiring DC power from the AC mains. So such type of applications where you require DC power but the supply is AC, in that case we required the rectification principle. So what are the types of rectifier in general? So we can classify the rectifier as uncontrolled rectifier or controlled rectifier. Uncontrolled rectifier are using the diodes which are producing the output which is in uncontrolled manner, fixed output. And the control rectifier will be using the thyristors or silicon controlled rectifiers for producing the variable output. Again, this can be half wave or full wave depending upon how many cycles of the AC input are used, whether it is used one half or both the halves. That will be classifying the rectifier as half wave rectifier or full wave rectifier. So we were discussing the half wave rectifier in the previous lectures. Now we will focus on three phase. Now why we are going with three phase? Because of certain advantage, that is higher power capability, smoother DC output because you will have lower ripples, and it is more common in industrial application as compared to single phase, and the transformer utilization factor is also better. So three phase system has certain advantage. When we talk about the three phase, it is always the balanced three phase system where you have three phases, VA, VV and VC. These are the voltages of the three phases. They are differ from each other, having with a phase difference of 120 degree. The magnitude remains the same for each of the three phases. So we can say that it is a balanced system. So when the magnitude is same, we say it to be a balanced system. And for the positive phase sequence, we can take the ABC phase sequence. So the benefit that we get from the three phase, we will be having the constant power flow. It will be a balanced system. Efficiency will be higher and the harmonics will be reduced, and we can get the better regulation. Three-phase system provide approximately √3 times more power than single-phase for the same conductor material, making them ideal for industrial application. So it is about root 3 times. When we talk about root 3, it comes to be around 1.732 times more power we can get it as compared to the single phase, keeping the material same in order to have a proper comparison. And hence the three phase system are having greater efficiency as compared to single phase. So when we talk about the three phase rectifier, they have a certain advantage over single phase. That is, the better transformer utilization factor will be there. Ripple factor will be lower in the output. Higher power handling capacity will be there. Better efficiency we will get, and the harmonic content will be reduced. And hence we can do the applications as high power DC motor drives, which are the industrial applications, battery charger for larger system, DC power supplies for industrial application, electroplating and electrochemical process are the one where we will be using the three phase rectifiers. When we talk about the circuit configuration of these three phase uncontrolled rectifier in the form of half wave, so only one of the wave, positive wave of the one phases will be rectified, the other half will not be used. So efficiency will be less as compared to full wave. But yes, we will be using the three phase and uncontrolled. So uncontrolled means we will be using the diodes. So the circuit components, when we talk about, we see that there is a three phase transformer which can be star connected as the secondary. Three diodes will be there, one per phase, and load resistor will be there, and there is a common neutral point. So here we can see that there is a star connected. So when we say star connected, it means the primary of the transformer is star connected and the secondary of the transformer is also star connected. The other configuration we are having the delta star connected. So primary is delta and secondary is star. So here we can see that the secondary will always be in the form of a star connected system, because in star connected system, when we are taking, we have the neutral point. So this neutral point we required only which is present in star connected system. So the secondary will always be in the star form. And we can see that here we are using three diodes. So we will be having the three diodes in the secondary of the transformer. This will be used for the rectification, and hence we are getting uncontrolled rectifier. And at the output, there is a load register where we are tapping the power. Some of the key features of this circuit is basically it is simplest three-phase rectifier configuration. Is it uses only the three diodes. The commutation principle is natural, and there is a unidirectional current flow in the system. Circuit operation principle, if we talk about, then at any instant, the diode connected to the most positive phase will be conducted. So the diode conduction will take place one at a time. So the diode which is present as the most positive phase, that will be conducting. So only one diode will conduct at a time, and the current flows will be through the conducting diode and the load. So the current should flow in the closed path. So the diode and load together will form one closed path, and non-conducting diode will be reversed biased in nature. Now, if we talk about the conduction sequence in the phase R, Y, and B, then we can say that when omega t is lying between 30 degree to 150 degree, then the phase R will be in conduction. When omega t is between 150 to 270, then phase Y will be in conduction, and phase B will be from 270 to 390. And again, the next cycle will start. So we can say that each diode is basically conducting for 120 degree in each cycle. So when we have one cycle of the AC wave, you can see that this is 120 degree conduction. The phase Y is also conducting 120 degree, and the phase B is also conducting for 120 degree. So this is the load voltage and current waveform for the half wave rectifier configuration. So when we see the input voltage, we are having R, Y, and B. These are the three phases that we have. And these three phases will allow the diode to conduct one at a time, and we will be having the half wave rectification. And we can see the load current and the diode current, which is shown here. So the key observation that we can do is that the output voltage is basically pulsating DC. So whatever the output voltage we are getting, it is not the fixed DC, but it is pulsating DC, and 3 pulses per cycle we will get, and hence the ripple frequency will be 3 times the fundamental frequency. The continuous current will be flowing through the load, for considering that it is a resistive load. If we talk about the input phase voltage, it is balanced system, which is a 3-phase system, and it is a star connected secondary. So the 3 phases R, Y, and B, they are having the equal magnitude, which is Vm, and there is a phase difference of 120 degree among the phases R, Y, and B. So here the Vm is basically the peak value of the phase voltage, omega, which is the angular frequency given as 2 pi f, and f is the supply frequency. So RMS phase voltage, whatever we are getting, is basically Vm by root 2. This is because it is a sine wave. So the output voltage analysis, if we do, then the output voltage V0 follow the most positive input voltage. So for the conduction from 30 degree to 150 degree omega t, we can get the V0, which is the output voltage along the resistive VR, is equal to Vm sine omega t. So average output voltage, if we want to conduct or find out, which is the VDC, then we need to integrate from 30 degree to 150, because that is the conduction. And here you have 3 by 2 pi as the time period, because 1 by 2 pi is the time period for one cycle, and because we have 3 cycle, so it is 3. And then we are integrating Vm sine omega t to d omega t. Ultimately, when we do this calculation, we find that VDC is coming to be 3 root 3 Vm by 2 pi. So this is the average output voltage. Since the maximum voltage is root 2 times the phase voltage, which is the V phase is basically the RMS phase voltage. So VDC, if we put in terms of phase voltage V phase in the previous expression, we get around 1.654 times the phase voltage. And if you take the line voltage, so line voltage is nothing but root 3 times the phase voltage, because it is a star connected network. So the DC voltage, if we talk, then it comes to be around 0.675 the line voltage. So this is in terms of phase voltage, this is in terms of line voltage, the DC. So alternative expression of DC, if we get, so we can say 3 root 3 Vm by 2 pi, which is approximately equal to be 0.827, the maximum value Vm. So we can represent this DC voltage in terms of the maximum voltage, the line voltage, or the phase voltage. The output voltage in RMS, if we want to find out, then we need to find the RMS quantities conducting from 30 degree to 150 degree. And as the principle of RMS says that we need to find the root mean square of the output voltage. So after doing the calculation with proper trigonometric rules and integration, we are going to find the RMS voltage as 0.84 Vm. So these are the steps, mathematical computations using proper trigonometric rules. We can find the RMS voltage to be 0.84 times the maximum voltage. Similarly, if the load is resistive in nature, we need to do the load current analysis. So average load current, which is the DC current, is nothing from Ohm's law. We can say that VDC by R, and VDC we have found out as 3 root 3 Vm by 2 pi. So we are getting the DC current as 0.827 Vm by R. We can also find the RMS load current, the peak load current, and average diode current similarly as IRMS, IM, and ID average. So IRMS is VRMS by R, IM, which is the peak load current, is VM by R, and the diode, since it is for the 3 cycles, which average we come to be IDC by 3. So we will get its corresponding RMS load current, the peak load current, and the average diode current of the circuit. We need to calculate the ripple factor. Ripple is the presence of unwanted frequency component in the system. So ripple factor quantifies the AC content in the DC output. So our output should be pure DC, but there are certain AC component which is also present, which is known as the ripples. This we have discussed in detail in the previous few lectures. So the ripple factor is nothing but the ratio of AC component of the voltage by DC component, which comes to be under root of V RMS square by VDC square minus 1. And if we compute for the three-phase half-wave rectifier using this principle, substituting the values that we got in the previous derivation, so that comes to be 0.183, which indicate that ripple factor is nothing but 18.3%. And it is significantly lower than the single phase rectifier, which is around 121% for the half wave. So obviously, the three-phase half-wave rectifier, whose ripple percentage is 18.3, is advantageous as compared to the single-phase rectifiers having 121% as the ripple factor. The form factor we can calculate as RMS voltage by DC voltage, and when we substitute these values, we get 1.016. We can calculate the peak factor or the crest factor as the maximum value of the voltage by the RMS voltage, which obtained to be 1.19. If we compare this with the ideal DC output, then the ideal DC output should have the form factor 1 and the crest factor as 1. So this is the deviation which we get from the ideal DC output. Three-phase half-wave rectifier has a form factor of 1.016 and crest factor of 1.19 compared to the ideal condition of 1 for the form factor and the crest factor. So it indicates very good DC characteristic because there is a small deviation as compared to the ideal values. Transformer utilization factor, again we need to compute, which is a measure of how effectively the transformer is basically utilized. So transformer utilization factor is the ratio of the power DC by volt ampere rating of the particular transformer which is under the study. So here for the three-phase half-wave rectifier, the DC output is equal to the product of voltage into current in the DC, and the rating of the volt ampere of the transformer is 3 times the phase voltage and the phase current of the transformer. Phase current RMS is nothing but the root 1 by root 3 times the RMS current, because each phase is conducting only for 120 degree. So transformer utilization factor from here we calculate and we find that it is coming to be 0.675. So around 67.5% we can say the utilization of the transformer. And if we need to compute the rectification efficiency, which is the power output by power input. Power output is in the form of DC, power input is in the form of AC. So the output power is VDC square by R, which is the power at the output. AC is VRMS square by R. And if we compute these values of efficiency, substituting the appropriate values of VDC and VRMS, so that gives 96.9% as the rectification efficiency. So the contributing factors, we have no power loss in the idle diodes. It is a purely resistive load we have taken and the good waveform quality we are getting. Practical consideration, we need to have the diode forward voltage drop, which will be reducing the efficiency. There will be certain transformer losses and certain losses in the winding resistance. We need to do the diode selection criteria, which is depending upon the peak inverse voltage. Peak inverse voltage is nothing but the maximum reverse voltage, which is measured across the non-conducting diode when one of the phase is at positive peak and other at negative peak. So we are basically conducting and finding the peak inverse voltage across the non-conducting diode. So peak inverse voltage is equal to Vm plus Vm by 2, which comes to be 1.5 times the Vm for this three-phase half-wave rectifier. So in terms of the line voltage, if we need to compute, because this is the maximum voltage, we are getting 3 by root 2 times the V phase. 3 multiplication is because we have 3 diodes. So V phase by root 2, which is for the maximum conversion to phase voltage. So that gives 2.12 times the phase voltage. average forward current is IDC by 3 and RMS forward current is IRMS by root 3. So in order to select the diode properly, we need to have this computation appropriate so that we know how much current we need to pass when the diode is under non-conducting zone. So transformer design consideration, we have the secondary winding which must be star connected to obtain the neutral point, and each phase will be carrying a current for 120 degree per cycle. So RMS current in each phase, if we compute, then it is IRMS by root 3. Primary winding, as we have seen, can be in the form of star or delta. So it has to carry the discontinuous current, and it will be containing certain harmonics due to non-sinusoidal secondary current. We will not have a pure sine wave. We will have non-sinusoidal secondary current. So harmonics will be there. So the transformer rating is given by 3 times the product of the V phase and I phase. And if we obtain the I phase as IRMS by root 3, then we'll get root 3 V phase IRMS as the transformer rating. We need to do the harmonic analysis. The output voltage will contain harmonics, which are non-sinusoidal frequencies with 3 NF, and these are the product of the integer multiple of n, which is 1, 2, and 3. And if you do the Fourier series expansion, then the output voltage will be having a DC component, VDC, and there are harmonics present with the integer from n equal to 1 to infinity. So here, if you see, the n integer which is multiplying with the frequency component will give you the harmonics. Generally, the dominant harmonics are having the third, sixth, and ninth harmonics. And if you have a 50 Hz fundamental component, then which comes to be 150 Hz, 300 Hz, and 450 Hz for the third, sixth, and ninth harmonic. We need to do the filtering to remove these harmonics using the low pass filter having the cutoff frequency around 150 Hz. And this can be passive filters, combination of LC. So design is very important depending upon what is the ripples present in the output voltage. The load may be resistive type, or it may be inductive, or it may be capacitive. So resistive and inductive will have the resistive component always. So it is a combination of RL and RC. When you have the resistive load, the current will be continuous and the current waveform will follow the voltage waveform, and it is very simple in doing the analysis. But when the load is inductive or capacitive, then here current will be more continuous in nature in case of inductive load, and there will be reduced ripple in the current. We will have the freewheeling diode which will be needed. This we have discussed very detailed why the freewheeling diode is required in the previous lectures. These analyses are little bit complex. In the capacitive load, we have the capacitor which is providing the filtering action, and we are having the discontinuous diode current. So we have more higher peak current, and the regulation is better in case of RC load combination. Some of the advantages of this circuit is being simple because you have only 3 diodes which is required. Ripples is lower. We have seen 18.3% as compared to 121% that is generally present in single phase. Efficiency is higher. Theoretical efficiency comes to be 96.9%. Why theoretical? Because we have not taken into consideration the other losses like diode losses or transformer losses. Transformer utilization factor is also good compared to the single phase. Commutation process is natural because no external switching is required in this case. Cost effective because fewer components are required than in case of full wave rectifier, because next lecture we will see this full wave rectifier. It is reliable, simple design because, and hence it enhances the reliability of the system. So these are the few of the advantages of this circuit. There will be certain disadvantage as well. So you have the neutral point requirement because transformer secondary must be star connected. If it is not star connected, you will not have this neutral point. Transformer utilization factor could be made much better, and unbalanced transformer may result in secondary neutral carrying the current. Peak inverse voltage of the diodes need reasonable reverse voltage rating. Harmonics will be there because input current may contain certain harmonics. Limited power, which is the lower power capability than the full wave. So full wave will have more efficiency. We will see in the next lecture. DC magnetization, transformer core may saturate due to DC component. So since we are having the DC component, so the core of the transformer may saturate because transformer has to operate on AC wave. Some of the typical applications of these three-phase half-wave rectifier is in the industrial, commercial, and laboratory applications. Industrial applications may be battery charging, DC motor drives, electroplating, and DC welding power supplies. Commercial, we can have in the charging circuit in the form of UPS, the LED drivers, telecommunication power supplies, and electric vehicle charging stations. Laboratory, we are using as variable DC power supplies, electronic equipment testing, and some research and development projects. Let us take one design example to understand this. Three-phase half-wave rectifier circuit where the input is having three phase and the line voltage is 415 volt, frequency is 50 hertz. Output we need to get 200 volt DC with a current of 10 ampere, and we are assuming that the load is resistive in nature. So what is the solution? We have to calculate first the transformer secondary line voltage, determine the diode current in the form of peak inverse voltage and other current, transformer rating we need to calculate. We have to design the output filter because the output may not have the pure DC form, and then we need to verify the performance parameters. So solution for the case that we have taken, since it is a 415, output is 200 volt with a current of 10 ampere. So line voltage is suitable and the DC voltage, which is 0.675 times the line voltage, and that gives to be 280 volt because we see the line voltage is 415 volt here. So this is too high and hence we need a step down transformer which is needed. So here we see the DC voltage we require 200 volt, but we are getting 280 volt. So step down transformer is the need. So which will be bringing down the voltage, and hence the load voltage in the secondary will be VDC by 0.675, which comes to be 296 volt. Transformer turn ratio that is required for the transformer, it is a step down transformer. So primary voltage by secondary voltage, which gives to be 1.4 times as the transformer turn ratio, primary to secondary. Now we calculate the diode ratings, that is what is the forward current, which is DC current by 3. So we have 10 ampere output DC current, so it is 3.33. Phase voltage is 296, which is the output voltage by root 3, it is 171 volt. Peak inverse voltage 2.12 times 171 volt, that is the phase voltage, which is 362 volt. And we need to select the diode having the forward voltage drop greater than 5 ampere and the reverse voltage greater than 400 volt. Load resistance, we need to calculate how much can be the maximum load resistance. So VDC by IDC, so that gives around 20 ohms. So you cannot have a resistor more than 20 ohms in the load. Performance parameters for these three-phase half-wave will have the ripple factor 18.3, efficiency around 96.9, and the form factor will be 1.016. The comparison table of single-phase half-wave rectifier, three-phase half-wave rectifier, and three-phase full-wave rectifier. This we will discuss in the next lecture, but we have already covered the single-phase half-wave rectifier in the previous lecture. And in this lecture, we have seen three-phase half-wave. So we need to compare the performance in terms of number of diodes, ripple factor, efficiency, transformer utilization factor, peak inverse voltage, the ratio of VDC by VM, and transformer neutral requirement is there or not. So we can see that compared to half-wave, three-phase will be requiring more diodes, which is 3, and the ripple factor will be reduced comparatively from 121% to 18.3%. Efficiency will be just more than 2 times, 2.5 times. So it is 96.9 compared to 40.6. Transformer utilization factor is also about 3 times. So 0.675 compared to 0.287. Peak inverse voltage, you can see around 1.5 times the maximum value. And here the ratio of VDC by VM is also improved. We don't have the requirement of neutral point in single phase, but we have the requirement of neutral in the three-phase half-wave rectifier. Now, when we will discuss the three-phase full-wave rectifier, again, it will be much better as compared to the three-phase half-wave rectifier. So here we don't require any neutral point in case of three-phase full-wave rectifier. So the key observation, three-phase half-wave significantly outperforms the single-phase counterpart. The three-phase full-wave offers better performance but at higher cost. So full-wave will be better but cost will be higher. And the choice depends on application requirement and the cost constraint. So how much cost is we can bear and what type of applications we are dealing with. Depending upon, we can go with three-phase half-wave or three-phase full-wave. So let us summarize what we have discussed. Is the key point that we have covered is circuit configuration and the operating principle. We have done the mathematical analysis of the voltage and the current, computed the performance parameters in terms of ripple factor, efficiency, transformer utilization factor. Practical design we have done, determine the advantages and disadvantage of this circuit. We have seen the application and design example as well. So the learning outcomes of this lecture are, we have understood the three-phase rectification principle, analyze and design the three-phase half-wave rectifier, evaluate the performance parameters and apply to practical scenarios. In the next lecture, we will go with three-phase full-wave rectifier, and then we will compute the performance parameters of the different rectifiers as well. Thank you for now. See you in the next lecture.